In this video, we're going to talk about continuous probability distributions. We're going to talk about some properties of them, and we are going to start with a basic type of continuous probability distribution, the uniform distribution. So recall, a random variable is continuous if there are infinitely many possible outcomes on a continuous scale. So some classic examples would be time, weight, height. Each of these are on a continuous scale with no gaps. We also usually model cost as a continuous variable. One type of continuous distribution that we'll focus on in today's lecture is the continuous uniform distribution. We've already seen some uniform distributions that are discrete. For example, if we roll a six-sided die and x is the value that the die shows, then x could be 1, 2, 3, 4, 5, or 6, and each of those values is equally likely. So it's discrete because it has a finite or countable number of possible outcomes, and it's uniform because each value is equally likely. So uniform, each value is equally likely. A continuous random variable x has a uniform distribution if it can take on any value in a particular interval and any outcome in that interval is equally likely, or any subset of the same length is equally likely. So let's look at an example. Suppose that you know that a bus comes exactly once an hour, but you don't know at what time. So you just showed up at the bus stop, and you don't know if it came half an hour ago or 20 minutes ago or 59 minutes ago, but you know it comes exactly once an hour. So if we let x be the amount of time until the bus comes, then the amount of time until the bus comes after you arrive at the bus stop can be described as a uniform random variable on the interval 0 to 60. So you could be really lucky and it could arrive instantly. You could be really unlucky and it could arrive exactly an hour from when you arrived, like maybe the bus just left. So x could take on any value from 0 minutes up to and including 60 minutes, and any value in that range is equally likely. It's continuous because there are no gaps. So, it could arrive in 22 minutes or 22.3 minutes or 22.307 minutes or whatever. The precision of this is only limited by the precision of your watch or timepiece. So we say that this is continuous on the interval from 0 to 60, a uniform random variable on the interval from 0 to 60. So let's think about what this distribution looks like. So we're going to describe this with a graph where x is our random variable and it's on the x-axis, and the y-axis is the probability of x. So take a moment to just think about, what does this distribution look like? How would you draw this probability distribution where every outcome is equally likely? So take a second and think about that, and we'll talk about it in just a moment. Okay, so this x is the random variable, the amount of time until the bus comes. You know it's going to come within the next hour, within the next 60 minutes, and here you are at 0 minutes. And each of these outcomes are equally likely. So because every outcome is equally likely, it could be here or here or here, the height of that distribution is consistent, it's flat. So this basically looks like a rectangle, is what the uniform distribution looks like. So uniform, if something is uniform on A, B, if something is uniform over the interval from A to B, the way that this is going to always look is going to be a rectangle from A to B. We know that if x is uniform on the interval from A to B, then the probability that x is less than A is 0. The probability that x is greater than b is also 0. This is an assumption based on the uniform distribution that the variable will take on a value between a and b, no other value, and every value between a and b is equally likely. And so again, any value between a and b is equally likely. So they all have the same height on that distribution p of x. So we'll come back to this example, but for now let's think about a couple properties of continuous distributions. So remember that one property of discrete probability distributions was that the sum of the probabilities was always equal to 1 if you add up the probabilities in a discrete probability distribution, the sum should always equal 1 or, very close with rounding errors. What about for continuous distributions? What would that relate to? So with continuous probability distributions, like the whole idea is that there's infinitely many possible outcomes. So there's infinitely many possible outcomes. What does adding up infinitely many values look like? Well, if you've had Calc or Calc 2, you might know that it is an integral. It's the integral. P of x is equal to 1. This is an integral, and you'd see it in calculus. It's what you get when you add up infinitely many values that are infinitely small. And if you have not seen this before, no problem. This is not a calculus-based course, so no problem. But one thing you may know if you have seen it, if you have seen calc, is that the integral is equal to the area under the curve. So the area under the curve, that's talking about the area here. And so the parallel in continuous random variables is that for any continuous probability distribution, the total area under the curve is always equal to 1. So whatever the continuous distribution looks like, if it's a uniform distribution or a normal distribution or just some other distribution, the area under the curve of the probability density function, the area under the curve will always be equal to 1. So this area is always 1, and I would like you to think about probabilities and area as like a related idea. The second property of continuous distribution is that the probability that x falls between two values, c and d, is always equal to the area under the curve from c to d. And again, this is true for any continuous probability distribution. If we're talking about, again, a uniform one or a normal distribution or some other distribution that's continuous, but we don't know exactly what shape it has. So for any continuous distribution, if we talk about the probability that the random variable falls between two values, c and d, then that probability is equal to the area under the curve of the probability function between c and d. So area between x equals c and x equals d is equal to the probability that x is between d and c. One odd thing about continuous probability distributions, if you think about, what is the probability that x is any precise exact value, any precise exact value. Let's say, let's just say this is 2.06. Who knows? So what is the probability in a continuous distribution that x is exactly 2.06? Well, that's the area of that line segment. So what's the area of that line segment technically? It's whatever this height is. It's the height of this, so this is p of x, times the width of this line segment. What is the width of a line segment? Geometrically, it is 0. So with a continuous probability distribution, the probability that we're any exact value is equal to 0. With a continuous probability distribution, we will only talk about being between two values. What is the probability that we're, greater than this value or less than that value or between these two values? That will be a non-zero probability, or can be a non-zero probability, because it has width, it has area. But for a continuous probability distribution, the probability of the random variable taking on an exact value, at least mathematically speaking, is 0. This is sort of a weird concept, so it's okay if it doesn't completely make sense. But, if we think about, say, the bus stop example, and we say, what is the probability that the bus comes after exactly 21 minutes and 12 seconds? What do we mean by exact? If we're saying it like in this way, in this mathematically precise way, that would mean exactly 21 minutes and 12 seconds, and not a millisecond over or a millisecond under, but exactly that, as measured by like some higher power, not by a human. And so what's the probability of exactly that value out of all the infinitely many possible values between 0 minutes and 60 seconds and 60 minutes? The probability of that precisely is 0. If what you mean is the probability of the bus arriving at 21 minutes and 12 seconds, and by that you mean between 12 seconds and 13 seconds, anywhere in that stretch of time, then that is no longer a 0 probability, because there is a range there between 21 minutes and 12 seconds and 21 minutes and 13 seconds. Again, kind of just an interesting thought experiment, but not the biggest deal. One way that you'll see that as coming into play is that for continuous probability distributions, it doesn't matter whether or not we put the equal sign. So the probability that x is between c and d, between x is less than c and is greater than c and less than d, is the same whether or not we include those or equal to signs. And that's the only way that this will really come into play for us. All right, let's talk about this example of this bus coming, and you've arrived. You know that it will come sometime in the next 60 minutes, but you don't know when. So first question is, we've already drawn the distribution, and we see that it has this rectangle shape here. So our first question is, what is the height of this distribution? So the height of this distribution, as a number, what is it? Our second question, what is the probability that the bus comes less than 10 minutes after you arrive? So what is the probability that the bus comes within that particular range? Next, what is the probability that the bus comes more than half an hour after you arrive? So what's the probability that the bus comes in this range? And finally, given that you've been waiting for half an hour, what is the probability that the bus will come in the next 5 minutes? So given that you are in this range of more than 30 minutes, what's the probability that the bus comes in the next 5 minutes? So think about each of these. Remember about the connection between probability and area. So probability and area. That the probability that x is in any range is equal to the area under the curve of that distribution. So think about those, and we will go through those together in just a moment. Okay, so let's start by thinking about the height of this distribution. What is it equal to? Well, we see that this is a rectangle. So we know this is a rectangle, and we know something about the area of a rectangle. We know that the area of a rectangle is equal to its height times its width, right? So what is the width of this rectangle? The width of this rectangle is 60 minus 0. The width is equal to 60. And so we know that 1 is the area under the curve, by definition of a continuous probability distribution. The height, that's what we're trying to find, times the width. The width is 60 minutes. And so if we're trying to solve for h, we could divide both sides by 60. And so that means that 1 over 60 is equal to h. So h is equal to 1 over 60. And just in general, if x is a continuous, uniform, random variable on the interval from a to b, then the height of the probability distribution, the height p of x, the probability of the probability distribution, is equal to 1 over b minus a, 1 over the width of that interval. Okay, what is the probability that the bus comes less than 10 minutes from when you arrive? So here is x equals 10, and so we're looking for the probability that the bus comes in that range between 0 minutes and 10 minutes. So there's two ways to think about this. One is, again, to think of this probability as area. The probability that 0 is less than or equal to x, which is less than or equal to 10, is equal to the area under the curve of p of x, that function, from x equals 0 to 10. And so what is that area? Well, again, this is a rectangle for a uniform distribution. So this area would be the height. The height is 1 over 60 times the width of now this rectangle. This rectangle has width 10 from 0 to 10, so 10. And so that area is 10 over 60 or 1/6, or, point 0.16 repeating, or 1.167 we could round it to. Another way, one comment here, again, with continuous distribution, less than or equal to and less than are the same. So when we said less than 10 minutes from when you arrive, that would normally correspond to less than 10 minutes from when you arrive. And again, for continuous distribution, these two things are the same because any precise value has probability 0. Okay, the other way to think about this would be to say, well, this is, for a uniform distribution, because all possible outcomes are equally likely, because all intervals of the same range are equally likely. We could also just think of this as the probability that 0 is less than or equal to x, which is less than or equal to 10, is equal to this interval between 0 and 10, 10 minus 0, over the total interval, 60 minus 0. So it's sort of just the proportion of time for a uniform distribution. So this is 10 over 60, or 1/6, just as we had above. Okay, what is the probability that the bus comes more than half an hour after you arrive? So here's 30 minutes. What is the probability that we're in this window of x greater than 30? So the probability that x is greater than 30, again, we could look at it in two different ways. One is to say, what is the length of this interval? The length of this interval is 30, or 60 minus 30 over 60 minus 0. The proportion is 30 divided by 60, or 1/2. So that would be one way to think about it. Our other way, again, would be to think about the length and height of that purple rectangle, the height being 1 over 60 and the length being 30. And if we multiply those things together, again, we'll get 1/2. So 1/2, or 0.5, is the probability that the bus comes more than half an hour after you arrive. Lastly, given that you've been waiting half an hour, what is the probability that the bus will come in the next 5 minutes? So this is saying, given that we are in this situation above, given that we're in this window, what is the probability that, okay, I've been waiting for 30 minutes, what's the probability that it will come in the next 5? So this is actually a conditional probability. So we're looking for, given that you've been waiting for half an hour, in other words, given that x is greater than 30, what is the probability that x is between the next 5 minutes? So x is between 30 minutes and 35 minutes. That is our conditional probability that we're looking at. So one way to think about that would be to use our formula. Conditional probability, that's the probability that both things are true, that 30 is less than or equal to x, which is less than or equal to 35, and x is greater than 30, divided by the probability that x is greater than 30. That would be just using the conditional probability formula directly. So if both of those things are true, if we're in this window of time, then that's actually equivalent to probability that 30 is less than or equal to x, which is less than or equal to 35, right? Because all of the time where x is greater than 30 includes that interval. And so this is divided by the probability that x is strictly greater than 30, probability x is greater than 30. And so what is that? We already figured out the probability that x is greater than 30 is 0.5, or 1/2. And the probability that x is between 30 and 35. So that would be a width of 5. So between 30 and 35. So 5 over 60. So this is the same thing as 5 over 60 divided by 30 over 60, or 1/2. When we divide fractions, we multiply by the reciprocal. So this is 5 over 60 times 60 over 30. We can cancel the 60s, and so we've got 5 over 30 is our final answer. We could also just think of that as saying, okay, let's go back to areas. I know, again, that I'm in this window. I already know that I have waited 30 minutes, so I already know that I'm in this window. What is the probability that I'm in this particular chunk of it? Well, that's 5 minutes. That's a 5-minute chunk out of this 30-minute chunk. And so that's another way to think about it, kind of just intuitively without using the formula. All right, let me give you one more similar example to do. Suppose that the length of a class is uniformly distributed and the class always lasts between 45 and 55 minutes. Let t equal the length of the class. So I'd like you to draw the probability distribution for t, find the height of this distribution, find the probability that the class lasts less than 48 minutes, find the probability that the class lasts at least 50 minutes, and given that the class has lasted 52 minutes, what is the probability that it will last 54 minutes or more? So pause and try those out. We'll talk about them in just a moment. Okay, so this is a uniform random variable, and it starts at 45 minutes. So 45 minutes is the shortest the length of the class can be, and it ends at 55 minutes. 55 is the longest that the class can be. And we assume that this is like the x or the y-axis, that it starts at 0. And we have p of t is now going to be how the y-axis is labeled. And so this is what the interval is, that this is uniform on the interval from 45 up to 55. So it's uniform on that interval. And because it's uniform, because any equally sized interval is equally likely, that means that it's going to have a flat top, that this is going to be a rectangular shape for this distribution. Furthermore, if we want to figure out the height of the distribution, again, we can use 1 is the total area under the curve, and that's equal to the height times the width. And so because of that, that means 1 is equal to, the area is equal to, the height is the thing we're trying to find out, times the width. The width under here is 10, between 45 and 55, so times 10. And that means that the height is equal to 1/10 when we divide both sides by 10. So h is equal to 1/10. And so 1/10 is the height of that curve. So h equals 1/10. The other way to think about it, again, is just that the height of a uniform distribution is always going to be 1 over b minus a. In this case, it's 1 over 55 minus 45, and again, that's 1/10. What is the probability that the class lasts less than 48 minutes? So this is the probability that now t is less than 48, but it's also going to be greater than or equal to 45. So this is the area that we're interested in, up to 48 minutes. If we included, the just probability that t is less than 48, if we included the stuff to the left over here, notice that all this probability that t is less than 45 is 0, because we're assuming with a uniform distribution that it can only take on the values between 45 and 55. Okay, so what is that equal to? One thing is that it's equal to the area of this little rectangle. What's the area of this little rectangle? It's its width times its height. What is the width? The width is 3, 48 minus 45. What is the height? The height is 1/10. So this is 3 times 1/10, or 3 over 10, or 0.3. We could also just do, this is equal to the length of the subinterval we're interested in, divided by the length of the total length that this could occur, and again, that would be 0.3 as well. All right, what is the probability that the class lasts at least 50 minutes? So the probability that t is greater than 50 is equal to the probability that we are in this half of the distribution. And so that is, so the length of this greater than 50 up to 55, the total end of the possible range. That's 5 over the length of the total range, 10. And so that is 0.5 or 1/2. Lastly, given that the class lasted 52 minutes, what is the probability that it will last 54 minutes or more? So at this point, the class has lasted 52 minutes. We know that we're in this range, so we can only possibly be in this range. What is the probability that it will last 54 minutes or more? That is so this is given that the class lasted 52 minutes, given that t is greater than 52, what is the probability that t is going to be greater than 54 minutes or more? So this is the probability that both things are true. Probability t is greater than or equal to 54 and t is greater than 52 divided by the probability that t is greater than 52. Given the definition of conditional probability, that's the probability that t is greater than, so if both of these things are true, then just this is true as well. That is a subset of the other. So probability that t is greater than or equal to 54 divided by the probability that t is greater than 52. And so what is that? The probability that t is greater than 54. This is just a length of 1 from 54 to 55. So 1 out of the total was 10, divided by 52. What's this length? From 52 to 55, that's a length of 3. So 3 over 10, and that will be equal to 1/3 when you divide that out. Again, we could also just think of it as out of what you already know that has happened, out of the unit of 3 between 51 and between 52 and 55, 55 minus 52 on the bottom, 55 minus 54 on the top. That is equal to 1/3. So we could think about it either way.